The Build Show Build Boston series is sponsored by Allura Fiber Cement Siding, Mitsubishi Electric Train US, Roseburg, Schuco USA, and Warmboard.
Hey, Build Show Build Boston. Steve Basic Architect here. Yeah, we're looking out that beautiful window there. We got insulation now. We got air barriers galore. Hopefully we have continuity. But guess what? Today is when we find out, because I got my new friend Sam here. Sam from Retrotec.
Hey everybody.
Now, Retrotec builds and makes blower door systems.
We do.
Correct? You're out of?
We're out of Everson, Washington.
Everson, Washington.
Yeah.
I can't say that's probably a thriving metropolis.
It's a big city.
It's a big city.
A couple of raspberry
probably a big
fields,
city in Washington.
Maybe a golf course and Retrotec.
Do they have a stoplight?
Yeah, I think they do.
Okay,
yeah.
So they have a stoplight. So it is a measure of a big city. So, well, I mean, I would love to stay. I've been playing around with blower doors for, I don't know, probably 30 years now. But why don't you take over, Sam, and tell us all the different components. Why do I care about a blower door? What does it do? What's my goal? Give me the whole spiel.
Sure. So the blower door itself is nothing new. Retrotec's been around since 1980, making these tools. It's just now, in North American building codes that we're just now starting to pay attention to that. It's like, oh, air tightness is important for a number of reasons, not just energy efficiency, but keeping the house comfortable, keeping each individual room comfortable, trying to keep a nice uniform temperature all throughout the house, because essentially what we're trying to do is keep the outdoors out and keep the indoors in. Okay. Right? Our air barrier is that defining point that defines inside from outside. So we want to keep that nice and tight. So a good quality air barrier is going to be like a Yeti cooler. Right. And that's essentially what you have here. It's an airtight, insulated box.
To the Yeti cooler example.
I mean, everybody knows what one is.
It's an easy example. You touched on a really good point, though. Up until, I would say, just a few years ago, we used to think R value, insulation, super insulation, and I think in at least the last 5 years or so, a lot of pressure has come on to air tightness and the understanding that we have so many houses now that have so much data. It's like air tightness is probably equal to or even more important than R value these days.
Absolutely.
Right.
And that can vary for different times of the year and different climates, but it's important everywhere.
Yeah, and for you doubters out there, right, that say, yeah, air tightness, Steve, house has got to breathe. Well, if you really believe that, just ask yourself, do you open the window and leave it open an inch, or every window in your house? I don't think so. You close them because you don't want your house to breathe. So you can leave the house needs to breathe argument in your house.
And with the air comes other things, humidity, pollen, things like that. If you live in a city, other pollutants that are outside, so you want to keep all that stuff out.
Yeah, it's funny, as an architect, I have a number of houses where I have clients say things like, that's the healthiest environment I know. I sleep the best. I dream more in that house. I have a couple clients that have like 2 houses, one that's a real energy efficient, one that's an energy pig that they live in half the year. And the wife loves to go to the energy efficient one. She goes, I sleep, I just feel better when I wake up in the morning.
Sure, I bet. I mean, with holes that we have in the house that air comes through, I mean, not only is there humidity and other pollutants, but critters that come in and might leave things in the walls and things like that. And eventually that makes its way to our lungs and it affects how we feel. So.
Now, do you have air tightness levels that, like, if I was a builder and I came to you and said, hey, Sam, what's a good house? What would you tell me?
I mean, a good house is one that is deliberately sealed. I mean, try.
I'm saying a number. Do you have a number? I mean, as an architect that's been doing this for a while, I didn't mean to put you on the spot.
No, that's okay. I usually kind of float around 5 air changes per hour if you can get there.
Well, you're a lot more liberal than I am.
But I see a lot of really bad houses in the Southeast.
Yeah, no, that's true. I'm sure.
And for existing structures, it's hard to get there sometimes. But,
coming from New England, I mean, we have some houses that are down in the like 0.16 range. But I tell people, if we can get under 1.5, I think that's a good job.
Yeah.
I think a great job is below 1, and if we can do under 0.6, which is the passive house standard, I think that's an exceptional job. So that's kind of my rating scale. I think if we're above 1.5, we're still taking some time to look for leaks, and you know, they're still probably available to see. You start chasing leaks below 1.5, it could be 1,000 pinholes.
Sure.
That we might not be able to find.
And it's easy to get there if you test along the way, like we're doing now. Doing an initial test and just kind of keeping track on changes of the envelope as the structure continues. The hard part is when you go back when the building is finished and try to fix things.
Yeah, and the beauty of this is everything that we do from here on out, you can see we're here, we have all of our primary air barriers, no drywall, no blown in cellulose. All those things are just going to add to it what Joe, my mentor, would call a tortured path, right? And kind of help diminish some of that air leakage just because it's not a direct leak anymore.
Sure. It's that path of least resistance.
Exactly. So you brought your whole kit of parts. I know you said, hey, it's a fan, it's a frame, but tell me a little bit about the pieces. I mean, it's called a blower door because we have a big blower.
Exactly. And it fits in a door.
And it fits in a door, so hence blower door. See?
Named appropriately.
Exactly.
But it's essentially 3 components. It's our fan, it's whatever we're having in the doorway to block that space. So we make a couple of things. We have a frame and a canvas that fits the doorway. There's also hard panels you can get. But there has to be a measurement tool to bring it all together. So that's our 2-channel manometer that we have that looks something like this. And as you're tearing things apart over here,
breaking it.
You'll notice that the fan, it looks a little funky. There's these different settings on there. So on that plate, there's 8 different plugs there. The thing about this is, in order for us to get an accurate reading, the pressure has to be just right in the fan shell.
Gotcha.
So say if we have a very tight house like we plan for this one to be, if the fan is running wide open, those blades aren't going to spin fast enough to take a reading, so we have to choke it down.
Right.
So that's where we use this plate and just put a small hole so we can get those blades spinning to take a reading. So
to get us within this prescriptive range of air moving across the fan.
So 50 pascals is our number that we test to for residential spaces. That's true across the board, whether if it's an apartment or if it's a standalone structure like this.
Gotcha. And depending on the direction of flow, we're either pressurizing the house or depressurizing the house, right? We're either pushing air into the house and trying to inflate the balloon and test it, or we're sucking the balloon dry and pushing the air out and testing it that way.
Yeah, the standards will allow you to do either way. When I can, I like to pull a negative pressure on the house because we have dampers for bathrooms and kitchen exhaust. So if you're going to pressurize the house, you're going to blow that stuff open, and that's not really leakage you want to count.
Right, but I think when you do a passive house, I think they require both, and then the blower door number is the average.
Take an average of the 2.
Because they want to ensure, the reason that you would do a positive test is that you're pushing all the windows against the gaskets. So you're basically improving the performance of the windows by pressure. The minute I turn that fan around and start sucking on the window, I'm pulling it away from that gasket. So they have to be really good windows to perform well on that negative pressure test.
Yeah, the house leaks differently in both directions.
Yeah, so it's always good if you're out there testing, have your blower door, just pop it out, spin it around, run the test again, and you'll get a really good understanding like, hey, is it really a good performer or is it an okay performer? So blower door, we can modulate the amount of flow going through. These just pull off.
They just pull right out.
So, and then these, I don't want to.
That's a fresh one, so you might have to pull a little hard.
All right, I'll let you. I don't want to break
You can just pop them out from the backside too.
I got you.
Just pop out like that. And
now, is there any order in which?
There is. If you have the manometer on, which we'll show you here in a minute, it actually has a picture of the fan. So you pick which fan you're going to use. We make several different ones. And then you choose, we call them ranges, each hole size. And it'll have a picture of what it should look like on which holes should be out. So, and that's important because that's how the fan was calibrated at the factory.
And that's what the manometer, so let's talk a little bit about manometer. We said manometer, there's a lot of people out here that probably don't understand what a manometer is.
So a manometer is a pressure gauge. It's a tool that we're using to measure air pressure. And that's really all it's doing. It's doing math to calculate our airflow. But it's called a 2-channel manometer because it's 2 manometers built into one housing pretty much. One side is reading our building pressure with reference to outdoors, so that's how it knows when we get to that 50 Pascal target pressure. The other side is reading the pressure in the fan. And at Retrotec, we try to make it easy. Everything's color-coded, so the red tube goes to the red cloth, the yellow port goes to the yellow fan.
So is it safe to say that dual channel, it's taking the reading across the building envelope, and then that tells you, okay, we've met the criteria to do the test. And then the second channel is actually the one that's doing the test.
Yep, so it's reading the pressure in that fan shell. And if we know fan pressure, which we do, we're measuring it, it's actually collected right here in these 4 parts in the middle. And if we know the area of the hole on the inlet side, which the manometer does, it's configured in all the settings, then we can calculate our CFM.
Gotcha.
And then from there, we can get our ACH 50 as long as we know the volume of the space.
And I know on bigger projects, when I was at Building Science, I mean, we did a church, we had like 4 blower doors
Yeah.
there. So these can run in tandem
Yeah,
on larger
so
projects.
we actually have a lot of customers that do large commercial buildings with this. The largest one I've done is 33 fans.
Wow.
Yeah, and we made them so that you'll see that there's a Cat 5 port on both sides here. So that's how the manometer controls the fan. It uses a Cat 5 cable to tell it what to do. So in from the manometer out to the next fan if you have multiple fans.
So it's like a daisy chain.
Exactly, and they're all getting that same command going the same rate at the same time.
Okay. So we have our air barrier intact. We want to seal up everything except for one door.
Right.
And that one door is where we do the test.
Or if we're doing passive house, sometimes you want to see what all the doors are doing. We actually make a smaller frame where you can use our duct tester fan in a window.
And we can use it. That's
so
really
you can
cool.
do that too.
Very cool. So in the door, you guys have your frame here.
Yeah.
Right.
So this is just an expandable frame. It's aluminum. It has a rubber seal that goes all the way around just to give us a seal in that doorway. Essentially what it does, it kind of replicates the same amount of leakage you would see in a doorway.
Gotcha. So it's not built to be perfect.
It's not built to be perfect.
It's built to simulate a door.
It's going to leak a little bit too around the where you put the fan in the shroud, but not a whole lot because the older frames, they leaked a lot more. We made them now so that we have seals that are continuous around the corner, so you can get it nice and tight for a house like this.
Gotcha. And I know some guys, you know, they'll get crazy. They'll tape.
Yeah, they'll tape around it. Yeah.
And they'll get all excited about that.
Sure.
And the shroud is nothing but this large piece of canvas or tarp that gets over that. It's got a big hole for the fan. You have the crossbars here that tie into the frame across here and basically hang that.
So the fan will hang from one. The top one just gives you some extra stability if you really have to crank that fan up if it's a leaky house.
Or if it's a taller door.
You don't want it to go flying anywhere. So we want it to stay put. And yeah, the cloth, just a few years ago, we started making these. I mentioned on this manometer that one side references the outdoors, so we got to have a piece of tubing that goes outside to read that, right?
Gotcha.
The cloth actually has that built in. So you just plug the tube into the cloth. You don't have to crawl through the hole and toss it out to the side anymore. So helps with the wind dampening too, because sometimes windy days can affect our blower door readings. So we try to get that under control as much as we can.
And I don't know why I remember it, but the gentleman that I refer to him as the godfather of blower doors, but Neil, when he threw the hose outside, he would always put a cardboard box over it.
Yeah.
And he would put it up on like a little brick or stone or something. And I'd say, why do you do that? He said, because you don't want the wind blowing across that. You want a nice, consistent reading at that end of the hose.
Yep.
So basically, don't put it out in the wind if you're out on the coast somewhere. Don't
and
throw
be
it out
careful
on the
not to
deck.
throw it in a puddle or something like that
Don't
too.
throw it in a puddle. So
This
it gets
cloth
blocked
kind of
off.
removes all of that. What it does is it breaks the tube up into 2 sections and then tees it at 2 ends, so it kind of slows down that wind velocity some.
Gotcha.
We played around with a bunch of ideas. We 3D printed a bunch of things that might work on the end, and nothing really worked well, but this is what we got the best results from.
All right. And then I see you have some other stuff over here
Yeah.
that you brought along.
So, you know, we make tools for measuring leaks, but we also carry some stuff to help find where those leaks are located.
Yep.
Blower doors are great for that. So, for example, if we take the blower door fan and we flip it to where we are pressurizing the house, we can use something like this fog emitter that will blow theatrical fog into spaces that you want to check on, whether if it's a roof connection or something down below around doors. And it really helps if you have somebody outside to see where it's coming out from. And so we call that blower door assisted air sealing.
Gotcha. Gotcha. All right. Yeah. Well, I mean, I think that's a pretty darn good explanation. And we could talk certainly more. I think we should take the equipment over there, and while we're installing it, you could talk a little bit more about the do's and don'ts of blower door installation, and then we can find out. I'm dying to see what the number is.
Yeah, certainly.
So why don't we head on over there, and we'll bring that gear with us.
All right.
All right, so we just had a great conversation with Sam of Retrotec. He's over there setting up the blower door. I figured before we jump in there and go over the install, I grabbed Mike Brown. Mike Brown is one of the owners of Advanced Building Analysis. He is a local energy rater. He's our energy rater for the project. So, you know, all of these projects, you would sit there and think, okay, we have a builder, we have an architect, but no, we have energy raters. It's a whole collaborative effort, right?
Absolutely.
There's a lot of things about a project like this. There's the getting it built, getting it approved, kind of. There's rebate programs, which Massachusetts has some of the craziest prices for electricity that I just learned last week. But we also have some of the very best rebate programs in the country.
That's true, yeah.
Tell us a little bit about Advanced Building Analysis.
Sure. We've been HERS raters since 2007, about the same time that the MassSave program has used HERS raters as a third party and an open market to help people out. So we'll compete against each other, different HERS rating companies, but it's all very collegial and we work together a lot too. It's all about maintaining consistent standards and helping all of our clients, builders, developers, homeowners, architects, understand what these standards are, how they'll be evaluated. In Massachusetts now, 87% of new construction in the last 2 years has been HERS rated in the residential side of construction. Wow. So we really are touching a lot of projects. It's not only the best projects like this, we're touching everything and really helping other people who maybe don't have Steve Baden on the team to figure things out. We have 3 main points of service. The first is when we are looking at plans, and we do energy models based upon plans and specs. And we use that with the HERS rating process to pull a building permit now. You have to show that you will have all of the mandatory requirements and the overall performance modeled to meet the requirements of code before you get a building permit. So we help people optimize their choices to make that happen. Then about this stage of construction, we're not quite there yet, we'll be looking at all of the insulation, verifying exactly what's there, not only what nominally was there, not just what you paid for, but actually what we can observe and record and say, all right, we're confident that's there. That's going to end up in our final energy models. Right. We're going to come back one more time when we're going to do whole building air tightness testing. Yep. We're going to do airflow testing for ventilation systems, and we're going to do duct leakage testing. We're also going to verify all sorts of installed features, lighting and appliances, heating and cooling equipment, ventilation equipment, hot water equipment. And all of this goes into a final confirmed rating of performance, which is used in Massachusetts to get your occupancy permit. Right. So we help people right from that design right through to occupancy. And like you as an architect, it's really rewarding for that, right?
Right.
We get to see things right through from a concept to occupancy.
Well, what's interesting is, you know, I meet a lot of builders and or architects or even homeowners and say, oh, I have a really good house. Well, how do you know? Right? Unless you're out here verifying. And kudos to Mike. He does a great job. He's an extremely good collaborative player on the team. I've done a number of projects with him. So if you're in the Northeast, Advanced Building Analysis, look him up. He's out here, like he said, he was checking on the insulation. He's not afraid to tell us hey Steve, we're not quite making it here. So there's a number of areas. We documented it. We're going to have the insulator come back. We're going to do exactly what we said we did, or we're going to do, and then you're going to come back and check it again. So, you know, he's third-party verification so that when we walk away from here and I say, hey, we did a good job, it's not guesswork. It's all been verified, and it hasn't even been verified by me. We have a third-party verification. And lastly, some of those rebates, they're not trivial.
No. So the MassSave Level 2 all-electric incentive right now, what this home is going for, is worth $25,000.
Yeah, and we just had that on. We just had that on a project that we hit 0.7. It brought them into that Level 2 with all of the other things that they're doing. the homeowner got a $25,000 check for those incentives.
There's other tax credits which are available. For multifamily buildings, there's incentives for passive house. We help optimize for all these different targets that a particular client may have, and we help them learn about all these different targets they might want to have.
Yeah, and it's hard as an architect. People say, "Oh, hey, what? Are there any incentives?" I was like, "Hell, I don't know. Those rules change almost annually."
They do.
Right. So having a team player like Mike, I could just say, "Give Mike a call."
Yeah.
And Mike has the answers.
Yeah, the physics don't change, and you know the physics.
The physics don't
but
change.
the rules are changing all the time.
The rules change all the time. But anyways, we're going to get those things corrected, Mike. Thank you for coming out today. Looks like we got the blower door set up over there. So let's talk about the setup and then run some numbers.
Sounds good.
So we caught up with Scott. Scott, how you doing?
Great, how you doing?
President of Excelis. I met the president. He's here. So Excelis supplies insulation components to insulators all over the country.
That's right.
And you get to say, I supply all the components to Jesus.
That's a big deal.
That is a big deal.
Nobody else can say that.
Nobody else can say that. I mean, Jesus owns Advanced Green Insulation. And, when people tell me, hey, you can't use spray foam, I said, well, Jesus made me do it. Right? So, I mean, Jesus can't be wrong, right?
Jesus is not wrong.
Jesus
it's a great product.
Wrong. It's a great product. So, we're about to do our blower door test. But I thought I'd grab you. We'd come over here and we talk about air barrier systems and, get a feel for what is this product, your confidence level in it. Obviously, you're the president of the company. I mean, you're not going to come up here and say, hey, it's the worst thing on earth to use. But for those following along here, we have our Zip R9 on the outside. That's all taped and sealed up. That's our primary air barrier. And then you can see each of the cavities is sprayed with a couple inches of the closed cell here. Now this is supplied by you guys.
Yes, it is.
And tell us a little bit about the foam that we have in here.
So this is the XLS 2000 with utilizing the 4th generation Honeywell blowing agent. It has an R value of 7.6. It is an air barrier at 1 inch, and it is also a Class 2 vapor retarder at 1 inch. So this can be used as a primary air barrier. You have it here as secondary. We'd feel confident, even if you took the sheathing off, that this would stop all the air.
That would stop all the air. And, I was just thinking about it. I was doing the math while you're there. So we have 2 inches of this. So we have basically R15. Then we have R9. So, I mean, we're at R24 here before we blow the remaining 3 inches of cellulose in that cavity to get basically about another R15 or so R13. So we're going to have a really good wall system here. And it'll be interesting to see. I mean, I'm assuming this is going to perform exceptionally well. My experience in the past, I've actually done tests where we have the sheathing, do the blower door test, and then do a skim coat flash of closed cell. And it usually accounts for about an additional 30% reduction in air leakage just by doing that flash.
It is a great air barrier. And it can fill all the little nooks and crannies that are difficult to reach with a fibrous product.
And it elevates that surface temperature
Correct.
inside our cavity. And it's a Class 2 vapor barrier?
That's correct.
Right, so we don't need to have a vapor barrier on the inside if we're using that.
Right.
So, all right, so I think we're about to get set up over there. Let's see what we got for numbers. All right, so Sam, you're already ahead of me there, buddy.
Yeah.
So we got the frame going in. Let's see if I can't give you a little hand here. This is just an aluminum frame that obviously has that rubber gasket. You could tighten it, and then it has these kind of extension locks that give it that last bit of locking pressure. But you're just trying to get it close because we got to apply the shroud and then reinstall that in the opening, right?
Yeah, we're just fitting it for size to see where we need to go to put the cloth on. There's a couple of different ways we can put on the cloth. Some people like to drape it over and fit it that way, or drape the cloth over a door and fit it that way. I just spread it out on the ground.
I was taught, we always put it on the ground.
So there's no wrong way. It all works.
Walked it over and set it in the door.
Just kind of wrap it like a present.
Go ahead. I'll leave you to it.
Sure.
I'm going to just play spectator here.
And it doesn't have to be perfect on that first try, because chances are you're going to have to go back and tighten it up a little bit more. And you want to leave a little bit of room for the cloth to fit around it.
Right. So,
I didn't tighten that top part.
While Sam is doing this, I'll just give you kind of a little 2 cents on blower doors. When I started out with Building Science Corporation, like blower doors we were using them to do building analysis back in the late 90s. So like Sam said, they've been around a while, but what I think is really interesting these days, Sam, is that a lot of builders, this has become a tool for them. Like I know a lot of builders here in New England and some out of New England that have their own personal blower doors. And it's because they want to just be able to throw it in, do a quick test, and get an understanding of where their performance is lying.
Yeah, I mean, if we care about air tightness, it's a good quality control tool.
Yeah.
And it puts a number on where we are and where we need to be. And okay, well, if my number's a lot worse after this particular trade left, I know where to go look.
Right. You know, and as an architect, and even more importantly, as a builder, right, I always tell homeowners and architects, if you're interviewing builders, hey, what's your air barrier strategy? How are you going to test? How are you going to verify that number? And if the builder shrugs his shoulders and says, I don't know, we never test, well, then maybe he's not the right guy, or he's the right guy or right gal that needs to get educated to understand why a blower door is so important, right? So it's, again, it's a pretty simple tool. You put it in and we fire it up. But the knowledge that we gain from this is just, you know, an exceptional piece of knowledge to understand how well our house is performing. So, you know, if you're a builder and you say, okay, how much does that blower door cost? Well, imagine how you stand out with clients if you say, hey, we have our own blower door test, or blower door. We do our own blower door test as the builder because we want to ensure that our air barrier strategy or the architect's air barrier strategy is in fact performing as designed and as specified, right? So yeah, it might cost a little bit of money for this setup. I'm sure Sam, you get on the call with Sam will hook you up with a brand new system. But you have to stop thinking in, well, how much does that cost, right? Because you're either a really good builder that cares about what they're doing and they care about enough to understand exactly what level of performance you're doing, or you're a builder that simply doesn't care about it and, hey, whatever the number is, who cares, whatever. We built the house for Jim and Sue. They'll be happy, have at it, right? So, my 2 cents.
We got juice.
We got juice.
All right.
I'll step aside here.
So now we have everything on. We have power to the fan. We have our manometer turned on. When you turn on this manometer, this is actually built on an Android platform. So if you've already used one of those products or have an Android phone, you're kind of halfway there.
Okay.
So there's 3 apps when you boot it up. One's to run the gauge, one's for reporting, and the other one is basically our user guides and how-to videos. That you don't need the internet to access. It's all built in. So if you're brand new, there's videos in here.
So you have a whole library of how-to
exactly
in that.
And it's all broken down into categories. So there's a video for how to set up the frame, how to install the cloth. So that way you don't have to hunt through one long video to see what part you need. It's
and you don't need internet service.
Don't need internet. It's built right in.
Got it.
The middle one I was talking about is our cloud. So for example, if we're a builder and we are doing a series of tests throughout the build, we can save reports for the same address as we go and see, you know, how we're maintaining that air tightness. So we have something to reference from the test before.
Record progress, basically.
Exactly.
Gotcha.
But we'll go ahead and just launch the gauge and get ourselves a number.
Okay. Now, prior to this, somebody had to develop the volume of air, cubic volume of air, right?
Yep.
So that we understand that, okay, we're testing it, but that testing is getting measured against the surface area and the volume.
Right. Right. So I mentioned before, this is a 2-channel manometer, so we're going to have 2 readings. One's going to be pressure, house pressure, if we get to 50 pascals, and the other one's going to be our flow. And we can read our flow in that CFM or air changes per hour.
Gotcha.
We'll go ahead and what we can do is we can just tap on that CFM, and if we wanted to change that, we can just tap ACH. There's a whole bunch of different metrics we can use to read air sealing or air tightness. We have them all in here, but if there's only 1 or 2 that you use, you can just hit a favorite and it puts it at the top of the list.
Gotcha.
That way you don't have to hunt for it.
Gotcha.
But we'll go ahead and choose air changes per hour. And you can see where the volume shows up in cubic feet. So
okay.
I think our volume for this house is 65,000 cubic feet. So we can just tap on volume there. It takes us to that menu. and we'll clear it and we'll enter that in. So now this number will be specific to this house.
Gotcha.
Cool. But the first thing that we want to do is make sure that our manometer and our fan are going to be set up correctly. We want them to match each other.
They're intellectually connected.
Right. So that goes back to that range setting that we want to go to. So right now there's a picture of an open fan, and we're set to a model 4000. This is a model 5000.
Okay.
So we want to get on the right fan. So I can just tap on that model number. It has all of our devices. Here's model 5000 here. I can favorite it for next time. That way it's going to be at the top of the list. Select it. And I'm expecting this to be a pretty tight house. I don't think we're going to need a whole lot of fan power to get to 50 pascals.
Okay.
Just by looking around, looks like the guys did a good job. So we'll just start at B4. That's just 4 of these little holes left open.
Which is half of them.
Exactly. But before we turn things on, there's something that we need to do called a baseline reading.
Gotcha.
So there's other things that happen in buildings that we want to kind of weed out from our measurement. Wind, stack effect. So we want to be able to measure that first so we can remove it from the equation later.
Right.
So it's like if you're going to weigh something, you're going to zero the scale out first.
Yeah. Now you don't want to do a blower door in a 30-mile-an-hour wind on the coast, but the reality is we're not on the coast. We're pretty well protected here.
Yeah.
But there's probably places that are going to be exposed. They're near the water, and you might have a 10-mile-an-hour sustaining wind that you're going to have to do a test in.
You just have to deal with it and do the best you can.
So this zeroes out those effects.
Yeah. So baseline reading, bias pressure, those are interchangeable terms. So we have a button here that says bias.
Okay.
And so we'll click on that, and this graph will come up. There's a record button. So we can just start recording the conditions outside.
Right.
We can see there's not a whole lot of activity out there. This little yellow line is staying stable. If we were on the leeward side of the building, we had some gusts, we would kind of see this thing start to go up and down a little bit.
Right.
On a day like today, 30 seconds is good. If it was a windier day, maybe a minute or more.
Plus the fact that we're in the garage.
It helps.
We're in a protected environment that even if it is windy outside, it's not windy on the other side of this door.
Exactly. And if you don't really have a sheltered place like this to use, try to use the leeward side of the house.
Gotcha.
Windward side is going to give you more turbulence on that, on those pickups on the outside. But yeah, we've reached our 30-second mark, so we'll just go ahead and hit record again to stop. It'll ask if I want to save it. Yes, I do. And then we can go back. And so I can see that baseline there, 0.1 Pascal. Nothing's happening out there.
Gotcha.
So now we're ready to test. Now I can open the fan up, and I will match that same hole configuration that I see there. So just taking out these side holes, we can just drop them in these pockets here. Again, making it match the picture that I see there on the gauge. Yep. And this is just a magnetic plate, so it just sticks right back on there. Just make sure the logo is facing up.
Gotcha.
If it's a house I've never tested before, I kind of like to inch my way into it.
Gotcha.
Just to make sure I'm not going to pull anything apart, because 50 pascals of pressure is like a 20-mile-an-hour wind hitting the house at all 6 sides. So let's start at 25, and then we can work our way up. So
I'm with you, buddy.
I go there, and I'll hit set pressure. And then we have some hotkeys for these most common pressures that we use. So
Gotcha.
25 we usually use for residential duct testing, but for starting out for this, we'll use that. Especially if this were an existing home, I want to walk around and see, okay, am I smelling fireplace or mold or mildew or something like that? But new construction, you're really not going to see that. So we are getting a flow. Already at 25 pascals. So I've got these hotkeys right here. I can bump it up or down 5 pascals. So right now we can see that we're seeking 25 pascals right here in the middle of the screen. So now as I hit this, it says 30, 35, 40. I can keep going until I hit 50. And my percent speed, the fan is about at 90% speed. So we may need to go bigger. We may need to open up this fan a little bit more to give it more air so that it can reach 50 pascals. Because we're at 100% and we're not yet at 50. So I'm going to hit stop. And I'm going to open it up some more. So we're going to go from B4 to B8. Snap it back in there. We'll change it on the gauge. You just tap the picture of the fan, select B8.
So basically, it's wide open now. Does it have
Well,
a
it's not
setting
wide-
for?
it's not wide open,
Does it have a
just-
setting for pulling that off? Okay.
Yeah, just the
there's a
plate.
setting.
And then you can pull this ring off too to make it wide open.
Gotcha.
Yeah,
Understand.
but we'll see it. I think this should get us there.
Okay.
So set pressure, we'll just crank her back up to 50. Yeah, well, we should get there now. We're 50% in there. So you can kind of see it's kind of hovering around 50. It's not quite there.
Yep.
But if I hit this at button, there we go. That's going to give me the flow at exactly 50 pascals. So it's constantly extrapolating to make sure it's going to give me an accurate reading on channel
So
B here.
the air changes is not necessarily tied to the number we see
Right.
there.
It's
It's
perfectly
doing
at
math
50.
behind the curtain
Yep.
and giving us that number.
So let's say we were testing a really leaky house and we had the fan wide open and we couldn't quite
Right.
get there. That really comes in handy for that.
Gotcha.
So we're looking at about 1.15.
1.15.
Yeah.
We'll take that. We're not. I mean, we still have a bunch more to do here. You know, but I'll take that number for starter.
Yeah.
We're going to come in. We're going to tighten it up. Put in a whole bunch more of insulation, and you know, I mean, one of the things we can do, we can set up the theatrical fogger if you want,
Sure.
and see if we can go around and get any big holes.
Yeah.
On the
And
outside.
you know, I'm thinking about it now. One thing that's really important that we didn't mention is before you even set this up and run it, you want to make sure all your windows and doors are shut and latched. If it's a finished house, you want to make sure all your interior doors are open because you want an even uniform pressure all throughout the house. And those doors kind of act like dampers. So you want it all to be connected.
So is it, I mean, have you ever done it? I remember we used to we'd crank that up to 75 pascals.
Yeah.
And then we'd just walk around and kind of fan windows.
Sure.
Because it was just a really quick, easy way to understand, okay, you know, because there might be a window that the tape failed or blew off or something, but we can certainly do that.
Yeah, we can open the fan wide open and get a lot more air flowing through here if we want to.
Yeah, if we want to fire that up, I'm just going to take a quick walk around.
Okay. Just a theatrical fogger that we use to find leaks in buildings. So as we're pressurizing the building with the blower door, we can see that fog escape where there's leaks. So really all you do is just hold a button down and you can use this hose to direct it to certain spots. So if there's a specific detail you really want to pressurize and hit with smoke, you can have somebody else on the other side of that wall to see if it's coming out or not.
So we have a couple runners around the house here. They were checking on some stuff. One of them let us know that we actually had a tape seal installation downstairs in the basement that blew open. So we're actually going to rerun the test. Sam is going to go right from square one again and run us through those numbers, but we're going to rerun the test now that we've rectified that situation.
Cool. So we'll keep our same baseline that we have. Conditions outside really haven't changed. So we'll just go to set pressure, and then we'll go ahead and go to 50 pascals. And the fan kicks on by itself, and we'll stabilize once we reach that 50 pascal target. And if we hit this at button here, it will extrapolate the reading. So if it's kind of bouncing around 50, our flow will be the result of what it would be if it was right at 50 pascals.
So it did improve a little bit, but we're roughly at, you know, 1.0, 1.1.
Yep.
But again, we have a lot of work to do here, and so a little bit of improvement. We still got a lot more to do. Did you want to show us? Is there any other visual features here that we might want to see?
So one new thing that we've added onto this that we've never had before is a live graphing feature. So if I hit this graph button, I can see my pressure at channel A. And if I tap here, I can go back and forth from channel A and channel B. So going back and forth from house pressure to fan flow. So if I go to channel B, I can see what my air leakage is and how it's bouncing around. So if I want to go to my interval and make it, we'll make it a minute long. So we can kind of see from when we started until now. If I have somebody in another part of the house that's sealing as this is running, I can actually watch it drop and see how much it drops. So actually this would have been good to use if they were taping. We could have left it running and then watch it drop in real time to see what it did. So that way we can kind of record what leaks are at what level of severity compared to others.
Gotcha. So I'll tell you what, why don't we turn the fan around? You brought the theatrical fogger. Why don't we put that into some action?
Yep.
And we'll see. We have some guys running around on the outside. We'll see if that we can identify some more leaks.
Yeah, let's do it.
All right. All right, Sam. So we ran the blower door again. We got a slightly better number, but in walking around, we realized we had a pipe open here.
Yeah, open pipe.
It's always good to walk around, make sure all the windows are locked. Pipes that are vented through the roof that are basically wide and air open, make sure they're closed off. So Sam actually turned the fan around. We're pressurizing the house to 75 pascals. Watch what happens when he applies the fog test here.
Yeah.
So we can see that getting sucked in, and it's getting pushed out by the fan.
Right. So you can see right there in that demonstration, basically, Sam's dumping the air in front of it. The pressure of the fan over there, positively pressurizing the house, is pushing that smoke right up. And I'm sure if we were standing on top of the roof there, we'd see a little smoke coming out of that pipe.
Sure.
So why don't we seal this up? We'll spin the fan around again and yet do another number.
Sure.
Now, this is why I think this is a really good example as to why builders would want to have a blower door as their tool. You can see by putting it in there, doing a blower door test, getting a number, maybe as a builder you're not satisfied with it, you turn that blower door around and you walk around with a handheld smoke machine, you find pipes that are open or a window that wasn't taped or a blowout on a piece of tape like we found out there, and having your own blower door, it just makes you that much better of a builder. So let's go back over, we'll reset the machine, and we'll shoot another test after we tape up the hole.
Yeah, so what Mike found here was this corner of this barrier as it comes around just didn't get sealed well here. There's still an open spot, so there's a hole right here in the air barrier. So as we're still pushing on it with the blower door fan and we're putting some smoke to it, and we can see that smoke getting pushed through that hole and then to the outside. So I think if you're going to use a small smoke emitter like this, I think it's easier to see what's going on while you're pressurizing because it's getting pushed through and out to the outside instead of back into your face. So that's a good example there to show. So essentially what we have here is a small metal probe that's 1/16 inch in diameter, and we have it here underneath this bottom plate here because we thought we saw some smoke interacting with it, and so I'm connected a good amount to the outdoors here. We're depressurizing to -50, so as we depressurize the space, outside air is getting pulled in. And so this probe is picking up some of that air getting through the air barrier. So we know we have some leaks here because we're picking up almost half of the building pressurization that we have going on with the fan. So that probe is telling us that we do have a leak here across this bottom plate here that just needs to get sealed up a little bit better.
All right, so we did go around. We found a handful of leaks here, ran around. We're coming back to do yet another test. So hopefully we walk away here with the final number. So Sam, have at it, buddy.
Yeah, we'll just go to set pressure in 50 and see what we get.
Yeah, it blew open again.
Yeah, it's not as bad as it was, but it came down some. But we were at what, 1.07?
1.07.
Something came open some.
So we jumped over by one of the windows. This is an operable window. You can see I have their smoke machine. Could literally blow smoke up your butt. I know that joke's getting old. But I think one of the things we wanted to illustrate using the machine and also why we chose the Schuco USA tilt turn windows. You know, if you grab this And if I run a bunch of smoke here, and we're running a positive pressure test.
Right, so we're pushing on it.
Right, so we're pushing on it. But you can see here, none of that smoke is evacuating along those joints. It is all being retained inside the building. And, you know, I kind of knew that before, because I'll show you visual number 2. If we simply take the window and pull it open a little, I can feel the pressure, I can hear the whistle, but watch what happens when I let the window go. Right? The fan ramped up because we had a hole. Now you can hear the fan going back down, but the window is, or the pressure, positive pressure, is pushing the window against that gasket.
Yeah.
Right? And these have those triple gaskets. Now, the other thing that we did, Sam, was you worked with us to calibrate our air leakage in terms of a visual, right? So we opened the door until Sam saw the number double on the reading there. So that way there we could get a sense on what the air leakage was. And, you know, Mike Brown brought this up. He's already gone, but I'll give him credit for the information. I calibrated it. It's 3.5 fingers. So if I put my fingers right there, that's about the amount of air leakage that's happening in the house cumulatively right now. And so we're going to tighten that number up. So, you know, we're at 1.0, and it's still a pretty significant amount of air we're chasing there. So we got our work cut out for us, but the next time we do a blower door test, it will be better. All right, so we shut her down. We're about to wrap up. Sam's got his little handheld smoker here, and we're not here to blow smoke up your butt, contrary to Sam's activity here with his handheld smoker. But we are here to talk a little bit about the numbers. So I asked Mike to join us. We got Sam over here. Our number, 50 pascals, we're somewhere right around 1.07. There's some leaks we were chasing, some blowouts on one of the basement doors downstairs that has yet to be installed. We have it all taped off. It keeps blowing up, but we have a really good sense. For the sake of numbers, we're hovering around 1, plus or minus here, on our initial test. Now, that's just one metric that we can use. There's multiple metrics. I know, you came over, Mike, and said, well, what's the CFM number?
Right.
Because you don't care about the air changes per
And I
hour
don't know who
number.
calculated that volume.
Okay.
So I want to know what the CFM is, and maybe there was a mistake in the
Wait,
volume.
I thought I got the volume from you.
Wait. Right?
So garbage in, garbage out, right?
Yeah, exactly. The most direct number we can pull off the manometer is the CFM at the pressure. So you want to be able to log the pressure. You want to be able to log the CFM. You want to be able to log the amount of openings and the covering down here, because that's an important part of your measurement. If you have those 3 things recorded, then we can normalize by a bunch of different things. Right. We can normalize by volume. That's the ACH 50 we're all talking about. That's your 1 ACH 50 here. But we could also normalize by the surface area, which is another great way to do it. And we can even normalize by floor area, which is another way it's sometimes done. So what we're trying to do ultimately is predict air leakage too. If we want one metric that is the best indicator of how much leaks we should be expecting, it might be a linear dimension. And it'll be the linear dimension of all the cracks and all the joints in the building that you need to seal. Because that's the most important measurement if you're trying to predict leakage.
You know, as the architect, I'll confess, one of the penalties of this house is that as opposed to a fist, it's more like a hand.
Yeah.
So we have a lot of linear footage of exterior wall here, as opposed to you want to build a cube for the perfect energy efficient house.
Right.
But I know we're roughly at, I think, about 430 linear feet of exterior wall on the conditioned space. Right. That's a lot of leaks up on top. That's a lot of leaks at the mud cell. It's a lot of challenge to take on.
You made it tough on these guys to get their ACH 50 limit because of the shape of the building.
The building, right.
Yeah.
And so the way that we would report it as far as surface area goes is CFM per square foot of envelope area. That's how a lot of standards call for this. The commercial industry has been doing it forever. ACH isn't even a thing there because ACH just isn't a great metric because it doesn't put buildings of different sizes on an even playing field. I think Joe Stiebrick in one of his articles said air leaks through shapes, right? Air leaks through surfaces, not volumes.
Right,
so
and it's different shapes, right?
Exactly.
Yeah.
Yeah.
So by doing that, the square footage per square meter of surface area, or however you want to do it, it takes a 1,200 square foot house and puts it equal to a 5,000 square foot house that might have 500 linear feet of exterior.
As far as that leakage profile goes, yeah.
Okay. Well, there you have it. Retrotec came out. We have Mike out here from Advanced Building Analysis. So we got the pros out here. I'm just playing fly on the wall, trying to figure it out. But I'm going to walk away from here, get with the builders and say, you know what? We came out with a good number, but it's not good enough. So in the end, we're going to be a little bit better than that number. I was hoping, to be honest, for a little bit better number, but I'll walk away in confidence that, yeah, we'll get there.
This is pretty good.
This is just the first test.
It's just the first test. We still have a long ways to go in construction here. So thank you, gentlemen, for coming on out.
This was
thank
fun.
you, Mike. I appreciate all of your knowledge and your help. But yeah, Steve Basic Architect out here, Build, Show, Build Boston. We're signing off on our initial blower door test.